Hello, and welcome to the Oscillatory UAV Landing Platform designed by LAKHAZ Robotics. Unmanned aerial vehicles such as drones have become increasingly popular in various industries. A common challenge in this area is being able to land the UAV on a moving vessel. In order to help test the pilot's abilities as well as the performance of the UAV, it is important to create a realistic testing environment. Landing platforms do exist for this purpose. However, these tend to be very large and stationary, making them unsuitable aboard moving vessels. Due to this, we have designed a portable platform that allows us to relocate the platform and test aboard these moving vessels as a more accurate testing environment. Our platform has been designed to simulate the movement of different intensities of sea waves. The conditions of ocean waves can be classified under the Beaufort scale. This scale relates the wind speeds to wave conditions in the water. Our platform can simulate the motion of vessels navigating through the sea at different levels on the Beaufort scale.
This is the third iteration of our project, which aims to build upon the innovative designs of previous years. Initially, our focus was on validating and refining last year's oscillatory platform design. However, our team wanted to contribute to the progression of the project's design, so we decided to expand the project's scope to include a mechanism that would allow for the height adjustment, as the oscillatory platform had limitations in this regard. As a result, our project's scope was updated to not only validate the previous year's oscillatory platform design, but also design a mechanism that could displace vertically and have the ability to retrofit the oscillatory platform into its design. This mechanism was named the Z displacement platform.
Throughout the design process, LAKHAZ went through multiple iterations of the Z displacement platform. We went through 4 main revisions from our initial concept and slowly iterating and improving the design each step of the way. Our first main revision introduced 2 concentric rotating gears housed in a large track frame that would apply the vertical displacement through equal and opposite forces to 3 points on our lifting plate. The next major revision kept the essence of the mechanism the same, but saw the large track frame being reworked to save on material cost and weight. Additionally, due to the track frame being reworked, our team decided to add rollers to the frame to further support it and assist with the rotation of the gears. The third revision that our Z displacement platform saw was a complete rehaul of the track frame and the concentric rotating gears that aimed to further reduce material costs and weight. This would be our main working assembly, with the fourth and final revision being minuscule alterations such as hole diameters, adapting the lifting plate to accommodate the oscillatory platform, adding welded ribs underneath the lifting plate to aid in supporting the weight of the top platform, and lastly, fitting the oscillatory platform on top of our newly designed Z displacement platform. From there, LAKHAZ's plan of action was to manufacture and test both of these platforms to see if they matched with their testing hypotheses.
With the immense amount of manufacturing required to go forth with our plan of action, we ultimately landed on building the upper oscillatory platform as shown, utilizing various manufacturing strategies. We were able to use the water jet to manufacture all parts with a uniform thickness, while the mill and lathe were used to tackle more complex components. A plasma cutter was utilized to cut out the base structure, and various TIG and MIG welding techniques were used to connect these components. The majority of the manufacturing time was spent on the landing pad, which is made from 50-52 aluminum and was cut using the water jet, and the base, which is made of carbon steel rectangular tubing and was plasma cut and welded.
Nearly every component in the design was manufactured by our team, with the exception of the motors, gearboxes, U-joints, ball joints, and electrical components. Through the manufacturing process, we were able to overcome tolerance issues by utilizing various design techniques to limit the room for error. Some examples of these design techniques are the implementation of welded nuts in spaces where hand or tool tightening was difficult to reach. We also implemented various slotted or slightly larger holes for hardware installation within certain parts that require exact precision, such as the motors and gearboxes. Ultimately, we were able to develop a prototype to test and confirm the validity of our many hours spent analyzing and simulating cases of component stress and strain.
Our final design consists of the oscillatory platform sitting on top of the Z displacement mechanism with a new base designed. The total weight of the assembly is 56 pounds, and it is able to support a UAV up to 33 pounds, including additional takeoff and landing forces. The platform is able to replicate the roll, pitch, and heave of a vessel at sea and can be adjusted to simulate different degrees of motion based on different measures of the Beaufort scale. The oscillatory platform is able to operate up to a Beaufort scale of 8, while the Z displacement mechanism is able to operate up to a Beaufort scale of 3, being able to pitch and roll approximately 20 degrees and raise vertically 1.5 feet.
Ultimately, our platform is a valuable stepping stone in advancing the future of exploration. It will serve as a training tool for pilots and a means of further developing the autonomy of unmanned aerial vehicles. By providing a way for the safe simulation of challenging landing and takeoff conditions, we hope that this will help to refine future UAVs' capabilities, enabling them to better handle real-world situations. In the meantime, our design will provide a level and stable landing area for current UAV technology, allowing them to operate in a wider range of conditions. We would like to give a special thanks to our project advisor and project sponsor, Dr. Alex Ramirez Serran, and the Robotarium for all his help and guidance throughout our design process. As well, we would like to thank Sean Mason and Kevin Lee, along with the rest of the staff at the Makerspace for the invaluable guidance throughout our manufacturing process. Also, a special thanks to our pilot/drone videographer, Peter Wang, for the amazing footage that you see in this video. Thank you for watching our video. If you have any questions, feel free to contact us, and be sure to check us out at booth 96 of the University of Calgary's Engineering Design Fair.